want to go live. Hello. I don't know if people are here yet. I can't really tell. Looks like I have a couple people. Let me wait a couple seconds just to figure some stuff out. Okay. I believe there's a little bit of a lag from what I see to what YouTube sees, so just checking that it picks up these when I change my slides. Okay. All right, so I will just go ahead and get started. So thank you all for coming. This is the planetarium show today on Wednesday, February 23rd. My name is Caroline von Raesfeld. I'm a fourth year here at UCLA. I'm getting my degree in astrophysics. And I'm actually part of the Astronomical Society, which used to have sort of public telescope shows, basically right after the planetarium shows. So I've been going to those for a while, and I've always wanted to do one. So, for my presentation today, I'll be exploring sort of the curious case of neutrinos. So I'll be exploring the history of them, how they were discovered, and then some of their really unique properties. And then hopefully I'll be delving into sort of some of their recent uses in astrophysics research, such as what they can tell us about supernovae, or the sun, or maybe even dark matter. So if you've never heard of neutrinos before, I'll try to give a bit of background on them, but also feel free to ask any questions in the chat. I'll sort of monitor it periodically through the presentation. Okay, and then after the presentation, I'll be taking you all through the night sky with a virtual software stellarium, which is really great because you can sort of customize how you see the night sky, the hours, locations, etc. So let's get into the presentation, the curious case of neutrinos. Right. Sorry. Okay. So the neutrino as a particle was actually hypothesized in the 1930s by physicist Wolfgang Pauli. And basically, there was this issue concerning the decay of a neutron into a proton and electron, where the reaction actually didn't conserve energy and momentum. Therefore, he sort of concluded there was some other unidentified particle that was necessary to be able to conserve energy and momentum in the reaction. So he hypothesized that this new particle had to be very, very light to conserve mass, as well as be neutral to conserve the charge in the reaction, since the neutron is neutral and then the proton and electron, they'll cancel out each other's charge. So these specifications led to Enrico Fermi referring to it as a neutrino a couple of years later. I think it was at a conference, which soon became pretty widely used. In Italian, that means little neutral one. And so Wolfgang Pauli also hypothesized that the neutrino would be very, very hard to detect. And it took until the 1950s for the neutrino to actually be detected experimentally, I believe. Change the slide. Okay. So the actual observation of the neutrino, the first observation came in 1956 by physicists Cohen and Rains. I don't know if you can see my my mouse. I'll assume you can't. But they essentially had set up a lab in South Carolina to observe this reaction right here, which is called inverse beta decay. So essentially, what happens in inverse beta decay is a neutrino will hit a proton, and it'll turn into a neutron and a positively charged electron, which is a positron, this E+ thing. So that's the sort of reaction for it. And what Cohen and Rains actually observed was sort of these very specifically timed signals from the neutron and then the positron. Basically, there's like a little bit of separation between them, and so depending on the timing, you can sort of figure out that these signals could only come from a neutrino hitting a proton. So they then sent this little telegram to Pauli to tell them they'd found the neutrinos. He hypothesized, say, we are happy to inform you that we have definitely detected neutrinos from fission fragments by observing inverse beta decay of protons. And I think Pauli responded sort of back to them like, oh, thanks for letting me know. And then I think he said, everything comes to he who knows how to wait. which I thought was kind of funny. Then what was actually equally interesting about this discovery was that they found the antineutrino. So in this reaction here, the bar over the nu is for neutrino, but the bar over the nu means antineutrino. So they discovered essentially that the neutrino has separate antineutrinos. So sometimes particles are their own antiparticle, but this is actually found not to be the case with neutrinos, which is a bit of an interesting sort of discovery. So actually, inverse beta decay is still a pretty common technique that's used to study neutrinos. And we'll explore it a little bit more later in the presentation. Sorry. So this was a pretty major discovery as it expanded our understanding of the fundamental particles and what sort of constituted our universe. So, neutrinos continued to be pretty interesting scientifically in, the second half of the 20th century. Essentially, we knew these particles existed, but there was a lot we had no idea about in terms of their properties. It was sort of successively found within the next decade and a half that the neutrinos found in the Cohen and Raines experiment were actually electron neutrinos, or electron antineutrinos, which usually occur in reactions with electrons or positrons. But actually, they also found, or sort of other experiments found, that there were other neutrinos that were associated with other fundamental particles called the muon and the tau. Oh no, I haven't been. Sorry. So yeah, here are the different neutrino flavors. We have electron neutrino, muon neutrino, tau neutrino. Each of these have their own separate antiparticle. So like the actual electron antineutrino, muon antineutrino, etc. So it was originally the idea that each of these neutrinos would actually have no mass, since no experiment had seen any indication of it. And this property fit pretty well into the standard model of particles, which was becoming really prominent in the later half of the 20th century. So due to the assumption that these particles had no mass, it was assumed that the flavors were invariant, meaning they sort of couldn't change between flavors, like an electron neutrino couldn't become a muon neutrino, a tau neutrino couldn't become an electron neutrino, vice versa. But this was soon to be disproven, actually, in the solar neutrino problem. So, one particularly curious issue that came up was in this experiment called the Homestake experiment. And in this experiment, astrophysicists Bacall and Davis aimed to study sort of how neutrinos were produced in the sun's nuclear fusion process. This is called, we sort of call these solar neutrinos, if they're produced in the sun. So they had set up this experiment to count the number of electron neutrinos produced in the sun, and they ended up only seeing around 1/3 of the number that they expected. So this sort of posed the issue, was the experiment wrong, or was it our understanding of neutrinos that was wrong? So, of course, in our assumed model, neutrinos had no mass, so they couldn't change between one another, so we sort of assumed that they would stick the same flavor the entire time. And, of course, physicists weren't so keen on changing that model because it agreed pretty well with the standard model, which was becoming pretty standard. So, but after actually more and more experiments, it seemed that the model wasn't quite holding up in that area, and rather that each neutrino flavor had mass, and then it also oscillated between flavors. And the reason you were only seeing 1/3 of the expected counts was essentially that the original experiment was designed only to detect electron neutrinos, and so you wouldn't detect if other neutrinos if they would change flavor. So if the electron neutrino changed to a muon or tau neutrino during their path to Earth from the sun, you sort of wouldn't be able, your experiment was no longer able to detect those. So I won't go too deeply into this because it could take up sort of a whole presentation. But I encourage anyone who's interested in this to look into it. It's called the solar neutrino problem. And it was sort of solved in like 1998, 2002. And one of the detectors that helped solve it was the Super Kamiokande collaboration in Japan. So definitely look into that if you're interested. I just wanted to highlight some of the sort of unique nature of the particles. Okay, so essentially, we now know that neutrinos have mass, and as one travels, it may oscillate to a different flavor during its path. So these are some of the like major advancements in understanding neutrinos, but there's certainly a ton more to actually explore in their realm. So now I want to go a little more into sort of current methods and what we're kind of looking in now in terms of neutrino research. So let me get to the next slide here. Okay, so I'll go a bit more into some of the questions we're considering now that these other issues and questions have been addressed. So kind of what does what we know now mean for astrophysics research? So essentially, we know our model is somehow incomplete. We want to know how we can explain the sort of discrepancies or how we can improve our model. So something we're actually still working on is the idea that neutrinos have mass and what that means for the standard model. So do we have to modify our current model or is there something else that we're missing? Sort of involved in that is, are there more neutrinos? Are there different flavors? Are there exotic neutrinos like this hypothetical sterile neutrino that is proposed to only interact with the gravitational force? Some think that the sterile neutrino could explain the phenomena of dark matter. So that's an interesting sort of angle. And neutrinos have become really prominent in astronomy as they're a really interesting way to observe things like the sun's core or cosmic rays produced in the universe, or how supernova happen, sort of the stellar death, how that creates like black holes, neutron stars, and then just other sort of unknown phenomena. So much of astronomy research has in the past focused on the electromagnetic spectrum, i.e. optical light, infrared, radio waves, but actually studying neutrinos opens up sort of a new way to observe processes not sort of through the lens of electromagnetic radiation. And studies of neutrinos are often used to complement electromagnetic observations. And the field is sort of now colloquially called multi-messenger astronomy because you get sort of information from all these different messengers. Get to the next slide. Okay. I also just wanted to highlight a couple of interesting neutrino experiments currently going on and sort of like upcoming ones. So there's definitely a lot of really interesting ones happening in neutrino physics, from like trying to find sterile neutrinos to looking at the sun's core, or even using neutrinos to detect supernovae. So I've highlighted just a couple of these here, though there are like dozens of detectors working to further understand neutrinos and their properties, both sort of in progress and upcoming. As well, there's many that are looking at new ways of detecting neutrinos. So I think I previously said that a lot of neutrino detection been done with inverse beta decay, but there's a lot of different sort of reactions we're kind of looking at now. One's like coherent elastic neutrino nucleus scattering, where a neutrino will just hit a nucleus and scatter elastically. That was first observed in 2017, so that's becoming more prominent. But essentially, it's a really interesting field that sort of advances in technology have been really allowing us to explore a lot more deeply. Okay, so on the left here, I put a diagram of the Ice Cube Neutrino Observatory, which is actually located in Antarctica. So this observatory was the first to detect high energy particle events that came from outside our own solar system back in, I think, 2013. So these kind of neutrinos from outside our solar system are really unique signals since they come from like very powerful cosmic objects like black holes or pulsars or active galactic nuclei. And then in 2017, I believe they detected a neutrino from a blazar that was located like 5.7 billion light years away. And they were actually able to localize the source of the neutrinos to figure out that it came from like that specific blazar, which was actually, I think, the first time a neutrino detector had actually like found an object in space. So that's a really interesting application. As you can see, there's like the sort of laboratories on top of the ice, and then a lot of the detectors go super deep into the ice. As you can see, here's like the Eiffel Tower for comparison. Quite a lot of Eiffel Towers there. So it's a very large experiment, very, I think, international collaboration, and it's continuing to search for these signals and other signals like it, as well as sort of delve into exploring cosmic rays and dark matter. Then, on the upper right here is Super Kamiokande, which is located in Japan, which I mentioned briefly earlier as being one of the experiments which found an explanation for the solar neutrino problem. So this detector was also one of the detectors in 1987 to see the neutrino signal from the closest recorded supernova since the telescope was invented, I think. It's an odd fun fact, but that was supernova 1987A. The neutrinos from this supernova arrived about 2 hours ahead of the actual light from the supernova, since essentially neutrinos will pass through the sort of supernova cloud a lot easier than light. So photons usually get like blocked by things like dust, but neutrinos will not. So they can arrive to us much faster. And this detector is actually currently being upgraded, I think, to Hyper Kamiokande, which I think will start taking data in 2027. So that's something we have to look forward to. The other experiment on the bottom right is the Sudbury Neutrino Observatory in Snow Lab, which is located in Canada. So the whole lab hosts a couple of really interesting experiments, like the upcoming, I think, super cryogenic dark matter search. But Snow Plus, which is this funky-looking detector, is their latest neutrino experiment. It actually has an overarching goal of understanding whether the neutrino actually is its own antiparticle or not. But it's also working to understand things like the sun's core and the processes that take place in it via neutrinos. So those are some interesting experiments to watch out for, but there's definitely a ton more if you just like Google search neutrino experiments happening right now. There's a lot going on there, which is really interesting. So now that I've introduced some of the current experiments and what kind of things they're looking for, I'm hoping to delve a bit deeper into the actual science that motivates this work. So first off is neutrinos and supernovae. So I know I've been talking a bit about supernovae and neutrinos, so I wanted to go over the sort of science behind why it's so interesting. So core collapse supernovae explosions happen when specifically massive stars die, and they'll release just a ton of neutrinos. And these core collapse supernovae produce either neutron stars or black holes, usually. And essentially, astronomers are really interested in how massive stars form those objects. So a major area of research is essentially how these supernovae happen, like what goes into the star dying, how does it form these black holes. So essentially by looking at the neutrino signals from these supernovae, we can sort of begin to understand things like how many neutrinos are produced, and like in what ways are they produced. So there's actually this thing called neutrino heating, which many think play an important part in these explosions. So learning more about that will definitely tell us a lot more about what goes into the stellar death of these objects. So supernovae actually really rarely happen in our own Milky Way galaxy. The only neutrinos we have ever seen from a supernova is SN 1987A, which I talked about a bit earlier. Kamiokande detected it. And the photos I've shown here are photos of the supernova. I think the one on the bottom is like a couple different wavelengths. I think it's like some visible and then some like radio infrared. It's a really cool picture, I think. But since neutrinos are really, really hard to detect among sort of all the other signals that are coming from the universe, we've been working basically to develop really, really sensitive technologies that can be able to see those signals from the neutrinos without like getting confused with like other signals from like cosmic ray backgrounds or other stuff. So technologically, it's definitely a challenge, but we really want to see supernova outside our own galaxy. So a lot of these new detectors are sort of gearing up to do that. That includes like Hyper Kamiokande, Ice Cube, Snow Plus, Xenon, Dune. There's a lot of them. And I think Hyper Kamiokande is supposed to be sensitive to supernova in like Andromeda or beyond. So that'll be really interesting to see in the upcoming years. Another brief, another application potentially is in the realm of dark matter. So sort of looking at what neutrinos can tell us about dark matter. This is, of course, a really large field in itself, so I'll just kind of review some main points. If you maybe have never heard of dark matter, essentially there's this issue that we don't know what makes up about 85% of the matter in the universe. That matter doesn't interact with light, only gravity, so that's why it's called dark matter. One of our hypotheses for this type of particle is a sterile neutrino, which would be a neutrino that only interacts through gravity. So this hypothesis sort of comes out of the discovery that neutrinos have mass, which essentially violated a bunch of laws of the Standard Model. So particle physicists are sort of wondering if there's some other like exotic neutrino that could help explain a lot of these issues we're having. Which it would be it would be a really nice explanation, but I think experimentally not too much evidence has been found for sterile neutrinos so far, although many experiments are searching for them. So there's still this issue, but we're sort of trying to rule out, is it, if we should consider modifying the Standard Model, if we should continue going with these experiments, if we'll find something. So I think it'll be really interesting to look at in the next couple of years. And then the sort of last science-y bit I wanted to talk about is this, the idea of solar neutrinos, which I touched on a bit earlier with the solar neutrino problem. And I wanted to focus on what these neutrinos can tell us about the processes that go on in our sun. So I just wanted to explore what some of the current solar neutrino experiments are doing. Essentially, these neutrinos can easily escape the sun's core, and they can do it much faster than photons, as you can see in this little infographic. Photons will kind of like bounce around, be deflected off of like ionized molecules, And it essentially takes like quite a while for them to get out of the core, especially. But neutrinos just sort of pass through quite easily. So they're a really great way to see what's like actually happening in the core of the sun in like real time. So one specific kind of thing solar neutrinos have been used for is looking at the processes of nuclear fusion in the sun. So essentially, there are like two main processes of fusion in stars. There's the proton-proton chain and the carbon-nitrogen-oxygen cycle. So the proton-proton chain is dominant in smaller stars, and it's thought that the CNO cycle is dominant in stars that are like a little larger than our sun. I think 1.3 times the size of our sun. And then we believe the proton-proton chain is the main mechanism of fusion in our sun, which and produces about 99% of our energy, of the sun's energy. Whereas the CNO cycle is believed to produce about like 1%. But a recent result in 2020 that I believe was published in Nature confirmed that the CNO cycle produces around 1% of energy, confirmed with observations of neutrinos produced from the CNO cycle in the sun. So this result is super interesting because it helps us understand more about what elements make up the solar core, and the sort of metals that are there, which can help us learn about the initial chemical composition of the sun, sort of at the time of its formation. Okay, so those are some of the main points I wanted to talk about. I'll do a little recap. So through this presentation, we've gone over the sort of hypothesis and then subsequent discovery of neutrinos, as well as talked about some of their puzzling properties and how they kind of mess with the standard model by having mass. We also looked at some current questions that are being addressed by looking at neutrinos, both out in other galaxies and then here in labs on Earth. We've talked about some types of neutrino experiments and some upcoming ones as well. And lastly, we delved a bit deeper into some of the unique applications of neutrinos. So I hope this presentation has sort of shown you how interesting neutrinos can be, as well as shown you a lot of different and unique ways we can explore the universe with unique particles like neutrinos. I know, like, when I was first introduced to neutrino astronomy, neutrino, like, physics research, I found it really interesting because I always felt, like, so surprised by the types of things neutrinos could tell us, and, like, the breadth of applications they have. And, like, looking into the future in multi-messenger astronomy, looking at neutrinos in complement to, say, like, in optical or infrared observations will be a really interesting thing to follow in upcoming years, I think. Okay, so thank you for listening to my presentation. If you have any questions, please leave them in the chat. But otherwise, I think we will now head over to Stellarium. It's about 7:40, so we can look at the night sky. Okay, let me move some things around. And I have to get Stellarium up here. Oh, thank you, Nithya. Much appreciated. Okay. Okay. Can we all see Stellarium, I hope? I have like multiple. Okay. So I'll start off by saying, okay, this is Stellarium. It's this web application that essentially shows you the sort of night sky. So what we're looking at right now is Los Angeles. The night sky of Los Angeles if if you could see stars in Los Angeles. um, so down here I have it set to 21. Actually, I can change. You can actually change the date and time in Stellarium. So I could say I want it to be like midnight. But I'll just set it. I'll do like 10 because I think a decent amount of stars are in the sky at 10. Okay. So to sort of orient ourselves, we can do it shows us the direction, so that's west, north. I'll go a little bit slower. We got east, and then south. So one thing that's great about Stellarium is that you have a lot of these sort of viewing options. So I could say I want to see, you can like change the Milky Way. I want to see, you can put in light pollution. I like to take it out because it's not very fun to look at light pollution. It has some like star lore and constellations. I think I can show the constellations. Yeah, so I can show their labels. I can also show their lines, which you can't get this on a normal night sky. And then I can also see, I can take this off. After them. I'll keep the labels on. As well, I think you can like zoom in sort of however far you want. And if you zoom in, you can often find it'll have art of some really interesting stuff. So this is it's a star, but it looks like there must be some gas and dust surrounding it. You can also find there's like the search window. I'll go to Andromeda right now. Oh, maybe I'll need to add some hours. Or subtract some hours. There's Andromeda. Oh, this must be Andromeda. Likely, yeah. So they have some galaxies, which is cool. And then there's also, I should be able to display, yes, this azimuthal grid. So if you're not familiar with how sort of astronomers use azimuth and altitude, it's sort of like latitude and longitude for the sky. So you can see there's like little lines like 280 degrees, or actually I guess you can't. Wish I could zoom in. You can see it down here. So there's like plus 300. And then on the side there's like plus 20. You see the equator is probably down here. Our like horizon is down there. Yeah, is at 0. So altitude and azimuth is most useful locally, which means if I was like talking to my friend who was in LA, and I told them, oh, you can see like Betelgeuse at this altitude, this azimuth, and they went outside like the same time I was outside, they'd be like, oh, I see it. But if I told that to my friend in like Europe, they would be like, I do not. It's like way different from what you see in the sky. So that's a local coordinate, meaning like it's local to where you are on the Earth. Whereas there are other coordinates that are more universal. So this is the sort of equatorial grid, and that is right ascension and declination. So I won't go too into like how we calculate it, but it's an absolute coordinate system. So if I tell my friend in Europe, like, oh, it's at this RA and DEC, it would find it. So as you can see over here, maybe it might be cut off. But when it says like 1 hour, 30 minutes, 58.83 seconds, and like plus 49 degrees, that's right ascension and declination. So that would be the same wherever you are. Okay. Cool. So now that we've gone over a bit about coordinate systems, I'll just go through some of these constellations. Okay. So if I was like, if you were at astronomy club or Astro Society with me, the first thing I'll probably point to is the Big Dipper, which, oh, sorry. I'm gonna start going a little slower. Okay, I had to look that one up. Okay, so Big Dipper is over here in the northeast. This is definitely viewable from the LA sky, or at least from the UCLA campus. You can see it pretty well. So we've got our little handle and the soup bowl. And what's really useful about the Big Dipper is if you trace these, sorry, I don't know how to, okay. You trace these two stars at the top of the Big Dipper, and you go essentially kind of just laterally, you'll find Polaris, which is the North Star. So directly north, you can just draw a line and find Polaris. And Polaris is at the end. It's the very last star on the tail of the Little Dipper, or Ursa Minor. So it's like kind of cut off, but you can see there's this like the arc and then the sort of little spoon bit. So that's really useful. It's a really useful one to know sort of how to get to the, because usually the Little Dipper is a lot harder to find in the night sky, especially in LA. So I like to start at the Big Dipper and then go to the Polaris, and then I'm like, oh, I know where the Little Dipper is. Another one that's you can usually see is Cassiopeia, which is usually, it's this like W form, sort of like a vertical W. It's supposed to be, I guess, Cassiopeia's throne, and that's one that's usually quite visible, and I like to look at. And then another one that's usually always visible is, find it, Orion. Okay, let me zoom in. Okay. Sorry, let me check the live stream. Okay. So as we can see here, here's Orion's belt. Oh, there was like a virtual shooting star. There's Orion's belt. That is usually quite visible in the sky. And there's Orion's sword, and then it's like shield over here. And then up here is Betelgeuse, or Betelgeuse. I don't know. Some people pronounce it differently. This is a very, very large red giant. I think it's the 10th brightest star in the sky. So that's, you can usually find Betelgeuse from Orion as well. There was, yeah, I think there is one, yeah. Sometimes you can see some of the nebulae down here, at least from a telescope. If you have your own telescope, I recommend looking at those. And there's Rigel. Another thing that's interesting is that, so there are these things called asterisms, which are sort of like, they're not set constellations, but they're like common things you can see in the sky, and one of them is called the winter triangle. So Um, the winter triangle is composed of Betelgeuse, Sirius, and then Procyon up here. Yeah. So Betelgeuse, Sirius, Procyon, and the winter triangle just means it's usually pretty visible in the winter. So there is an equivalent summer triangle, which is Vega, Deneb, and Altair. So if you go out in the summer, like June, July, you'll totally be able to see Vega, Deneb, and Altair. They're usually pretty bright and they form this little triangle. So I like finding those in the night sky. And Sirius is actually the brightest star in the night sky. So that's usually pretty easy to find. Okay. And if we look through here, I think you might be able to see this like faint thing of the Milky Way. Let's see, it goes from like southeast to over in northwest. It's definitely not visible in Los Angeles, but if you ever go out to the desert or like to the mountains on like a camping trip, you should be able to see the Milky Way. I recently went on a camping trip and I got to see the Milky Way, and it was really great. It's very you sort of like look up and you're like, what's that like fuzzy thing? And then you're like, oh, that's like probably the Milky Way. I think it's really pretty. And another thing we could find, which you definitely cannot see in SGR. I wonder if we can see Sagittarius. So the black hole, the center of our galaxy, is called Sagittarius A star. So I wonder if I can slew to Sagittarius. SGR A star came up. Will it let me go there? It's down on the bottom. I believe I can. Atmosphere chronal points. I can delete the ground, which is very useful sometimes. So if I go down here, well, it won't show anything, but that's essentially where the black hole at the center of our galaxy is, which is pretty cool. It's in the constellation Sagittarius, which is sort of how it's got its name. Yeah. Oh, and there's the moon. There's Jupiter as well. Right, let me put the ground back up. And you can look more at this. Does anyone have anything they would like to see? Put it in the chat. Totally welcome to. Astronomical calculations. I think I can see. I'm gonna see if I can see the. I should be able to show the. I can filter galaxies, marking equatorial grid. Galactic clearance. Star lore. I think there is a way to show like the actual constellations on here. There's meteor showers, exoplanets. Oh, some deep sky objects. Let's go back into Orion. You can see some of these. This is the 13th Pearl Nebula. Yeah, Orion Nebula. Which one's this? Flame Nebula. So yeah, there's some really interesting nebula as well. If you go around here, I like the Witch Head Nebula. I believe this is, so yeah, the Witch's Head Nebula sort of just, it's a lot of dark dust. Epsilon Pegasi, okay. we will go to Epsilon Pegasi. Oh, it's in the ground. There it is. Epsilon Pegasi. It's gorgeous. Ah, here's the summer triangle I was talking about. Big Altair. Where's Deneb? Where's Deneb? I think I lost Deneb. Oh well. You're welcome. All right. Okay. I think that essentially concludes my sort of mini traipse around the night sky. Please, if you have any other requests, put them in the chat. Or if you have any questions as well. If you have any questions about how Stellarium works, I think it's free to download. So if you ever want to download, just look around on your own free time. I encourage it. Otherwise, I think I will likely end the stream here. Okay. Thank you all so much for coming. Hope you learned something new. Hope it was an enjoyable Wednesday night. And this will be available to watch, I believe, after on the YouTube, if you ever feel like coming back to it. All right. I will end the stream then. Thank you all for coming. Hope you have a good week. Okay. Bye.